Hi everyone, welcome back to Useful Genetics. This is lecture 3M, where we're going to finally introduce the concept of dominance, learning how to think about phenotypes when an individual has two different alleles, is heterozygous. So we'll give you first a definition of dominance, and then we'll consider situations where this definition applies, and a large variety of situations where it doesn't apply, going back and reconsidering the same examples that we've been using in the last few lectures. So here's the definition of dominance. We consider using it anytime we have a situation where we have two alleles that give different phenotypes when they're homozygous. So the homozygote for one allele has one phenotype, the homozygote for the other allele has a different phenotype. If the heterozygote has the same phenotype as one of the homozygotes, then we say that allele, the allele that they have the same phenotype as, is dominant to the other allele. Now, the most important feature of this definition is that dominance is describing a relationship between two alleles. You can't apply the concept of dominance to a single allele. Dominance is, in a heterozygote, one allele is dominant to the other allele. So here's a simple example. These are P's, such as the ones Mendel worked with. So if the homozygote phenotype for the CY allele is the same as the heterozygote phenotype for CYCG, but different than the homozygote phenotype of an individual homozygous for the CG allele, G for green, Y for yellow, then we say that the Y allele is dominant to the green, the G allele. And that definition would apply in the example of our pink morning glories, where the heterozygote has the same phenotype as the blue homozygote, the homozygote for the wild-type allele, and the heterozygote for the wild-type allele and a non-functional allele have the same phenotype. So we say P plus is dominant to P minus. We might write this as P plus, using a greater than symbol, P minus. What about other situations that we talked about? Well, we talked about the ABO blood type system, and we considered three different alleles, A, B, and O. And the heterozygote phenotypes that apply in this situation are the phenotypes for individuals who are heterozygous for an A allele and an O allele, or a B allele and an O allele, because these individuals have the same phenotype as the A homozygote or as the B homozygote. So here we would say ABOA is dominant to ABOO, and ABOB is dominant to ABOO, because the heterozygote has the A phenotype or the B phenotype. What about if that doesn't happen? What about if the heterozygote has an in-between phenotype? Here I've drawn a plant where we have a tall allele with tall plants, a short allele with short plants, but the heterozygote is in between. They're kind of medium-sized. Then we don't use the word dominance. At least in this course, we don't use the word dominance. We would say that the alleles' effects are blended, or geneticists might say they were additive. We took or they were averaged in the heterozygote. Traditional geneticists have used the term semi-dominance or incomplete dominance. I recommend staying right away from those terms because they make you think that it's a kind of dominance, and it isn't at all. It's just a different kind of interaction. Here's an example. Here's our white-flowered morning glories, where individuals homozygous for the defective allele are white, individuals homozygous for the normal functional allele are deep blue, individuals heterozygous for the two alleles are an intermediate color. They're light blue. So we would say that the W plus and W minus alleles show blending in the heterozygote. What if the heterozygote has both phenotypes? Here I've drawn a flower with spots, and the spots can either be yellow or orange. And the homozygote for the yellow allele has yellow spots. Homozygote for the orange allele has orange spots. The heterozygote has both kinds of spots, yellow and orange. What would we say? We would say that both alleles phenotypes are seen in the heterozygote. And we would avoid the term codominance, which is traditionally used by geneticists, but is again very confusing because it implies that there's some kind of dominance going on in here. But there isn't any dominance, they're just both being seen. Now we can apply this relationship to thinking about our blood type alleles, where the ABOAB heterozygote displays both of the phenotypes produced by A and B. So they've got the blue sugars characteristic of type A, and they've got the pink sugars characteristic of type B. And their blood reacts to both antibodies. Their blood type is AB. What about cystic fibrosis? Well, here, just with one allele, we can see all three kinds of relationships, depending on what aspect of phenotype we're paying attention to. So if we look at the messenger RNA, we'd say, oh, we see both messenger RNAs. We'd see both phenotypes are present. If we look at the protein, we'd say, oh, it's blending. We've got half as much protein in the heterozygote, intermediate between the normal amount and the none in the mutant homozygote. But if we look at fertility or lifespan, we would say, oh, the normal allele is dominant to the delta F508 defective allele because in the heterozygote we see the normal phenotype. So what we've done, we've explicitly defined dominance as a relationship between alleles, a particular relationship where the phenotype associated with only one of the two alleles is seen in the heterozygote. We've gone back and reconsidered our examples, applying the concept of dominance or of blending or of both phenotypes being seen to our examples. And we've considered other ways that geneticists have traditionally used the term dominance, and we've said, don't do this, it will just confuse you. Coming up next, we're going to explain why we see dominance and get a better sense of how the kind of dominance that is so commonly seen in genetics textbooks, how that fits into dominance in the real world of real organisms. I hope to see you there.